Alright, in this video I want to talk a little bit about Kelvin. And the formula to get from degrees Fahrenheit or degrees Celsius to Kelvin is relatively simple. But I really want to kind of drive home the concept of maybe what Kelvin really is, because you're going to use this interchangeably a lot in different formulas and equations throughout this semester in chemistry, especially whenever you're doing anything that has to relate with like pressure and volume and temperature. You're going to always use Kelvin. And the reason why is because it's a greater judge of kinetic energy and the changes in the states of matter. What I mean by changes in states of matter is like, maybe going from a solid to a liquid to a gas, or on a wider scale is the best way I can think to maybe illustrate that on Kelvin, whereas like on maybe say degrees Celsius, your scale, or actually let me redo that and draw it a little bit better to show what I'm talking about. Alright, here we go. Kelvin. So let's say this right here is going to be absolute zero. This is absolute zero. And let's just say this is the boiling point of water right here. Or we'll call that the gaseous state of water. And this right here is going to be the liquid state of water. And this right here is going to be the solid state of water. If you look, the scale for Kelvin still has a ton more that it can go way over here, and in reality it still has a ton more that it can go this way. I just ran out of room on my board there. On the flip side though, degrees Celsius, the scale, whenever you reference it, it's much smaller. You've got solid, liquid, gas. So I mean, you can go down to absolute zero for Celsius, but it's such a large number that it's really not practical or convenient to use. So they've came up with Kelvin. All right, and Kelvin is basically for all intensive purposes just a scale where we can include absolute zero. What I mean by absolute zero is the complete and total lack of molecular movement. So let's say, and then a lot of times whenever you're talking about Kelvin and Celsius and stuff, you're talking about kinetic energy also. Let's say this is a molecule here. It's a horrible drawing, but let's just say it is, right? Let's say when these molecules, let's say they're water molecules, right? Whenever they bounce off of each other with a certain amount of energy, it's 15 degrees Celsius, right? If you get them to bounce off with enough energy and the temperature rises to 100 degrees Celsius, it'll change in a state of matter, right? Well, if you do the opposite of that and you slow them down to where they are not bouncing off of each other or anything else at all, period, they're just standing still, not moving at all, then you're said to be at 0 degree or 0 Kelvin. Let me just undo it. You're said to be at 0 Kelvin. So we know kind of what 0 Kelvin is a little bit at this point, right? But how do we get there? What are the means to get to Kelvin? Well, from Kelvin, basically, because this is, its starting point is at 0 molecular movement, anything in degrees Celsius is going to be a lot warmer than degrees Kelvin, right? That kind of makes sense. So if I have 10 degrees Celsius, that's going to be a lot warmer in degrees Kelvin than degrees Celsius, right? Because 0 degrees Celsius and 0 degrees Kelvin are two big, greatly different things, right? So it would only make sense that we would take degrees Celsius and add to it to get degrees Kelvin, right? Well, if you were thinking that, then you were absolutely correct. And let me do this in a different color even. So I've got what I have here, 10 degrees Celsius. So we're going to add 273.15. Pen's not working here, 0.15. Now, for most classes, you'll be fine with 273. The full number, though, is 273.15. So if you wanted to be super accurate with your measurements, you would want to include this 0.15. But for most classes, 273 is good. So you would say 10 degrees Celsius is 283 Kelvin, right? There's no degrees on this. It's an important observation. No degrees on that. And that's because it's a greater measure of kinetic energy, more so than degrees Celsius. It's a little bit more complex than that, but that's, I don't want to bog your brain down with useless information at this point in your career. All right, so 283 Kelvin is what you would do with degrees Celsius. Well, let's say you've got degrees Kelvin, right? Let's say we've got 200 and let me just scroll down. Let's say we've got 290 degrees Kelvin. Or just Kelvin, I said it myself, 290 Kelvin, and we want to know how many degrees Celsius that is. Well, you're just going to subtract 273 from that, and that's going to give you your degrees Celsius. So that's 290 minus, so that's going to be, what is that, 17 degrees Celsius. And it's literally that simple. If you're given Fahrenheit, right, you're just going to use the formula we learned in the last video, which is, basically, if you're wanting to solve for Fahrenheit, or if you're given Fahrenheit, you're going to take the temperature in Fahrenheit. Let's say we've got 60 degrees Fahrenheit. We're going to subtract 32, divide that by 1.8. That's going to equal blank degrees Celsius, and then we're going to add 273 degrees to that. Right? So let's just grab our calculator here. We've got 60 minus 32 divided by 1.8. That's going to equal 15.55. We're just going to add 273 to it. Plus 273. And we've got 288.55. So that's basically how you would get there. And that's about, or actually, 288.55. This was 15, I think, 0.55. This is what the calculator said, and then you add 273, and that becomes 288.55. That's about as complicated or as tricky as you can really get on going from, or solving for Kelvin would be to start at Fahrenheit and go to Celsius and then go to Kelvin. But it's important to know how to do Kelvin because you will use it a lot, especially in problems that involve pressure. Anyway, thanks for watching. Hope that helped.